Let's try to apply what we have just learned about Newton's third law of motion in a few situations that we have learned in the videos on the 5 different kinds of forces we can observe in a macroscopic situation. Let's say today you place a block near the surface of Earth, and because it has mass and is near the surface of Earth, this block here will experience a weight, right? So weight will be the gravitational force acted by the Earth on this block over here. So this weight over here, it's by the Earth on the block. So knowing Newton's third law, you know that if the Earth is exerting a force on the block should also exert a force back on the Earth, because any forces have to exist in pairs. If the Earth is now exerting a force on the block should also exert another force on Earth. And these two forces should be having equal magnitude but opposite direction. So what does that tell us about? If today we have an action-reaction pair, the action-reaction pair should have equal magnitude and opposite direction. So if you draw the free body diagram for the block, I'm focusing only on the specific parts that I'm interested in. There's supposed to be normal force, but I'm just focusing on the weight here because I'm talking about the weight here. So if my weight here is pointing downwards and this is a free body diagram of the block, we know that this weight over here is exerted by the Earth on the block. And because we know Newton's third law of motion, we know that for the free body diagram of the Earth, you should also observe a force that is exerted by the block on Earth. Because if Earth is exerting a force on the block should also exert a force back on the Earth. And we know that this should be equals in magnitude and opposite direction. So if the force exerted by Earth on block is pointing downwards, then the force exerted by block on Earth will be pointing upwards, the opposite direction. So if you draw the FBD of Earth, you actually draw this pointing upwards arrow to show that the block itself is actually trying to pull the Earth upwards. The small block here is actually pulling the Earth upwards using this force over here. And this force here has the same magnitude as the pulling force that is pulling the block downwards. Okay, you'll learn more about why the block can pull on the Earth in chapter 7 on gravitation later. Okay, next situation here, we talk about tension. So tension is exerted by the rope on the block. So if you draw the free body diagram of the block, you should have a tension which is along the rope but away from the object, something like this, right? So this force here is exerted by the rope on the block. So now if you know about Newton's third law of motion, you know that if we draw the free body diagram for the rope, if you draw a free body diagram, this dot here is representing the rope, then you expect a force by the block on the rope because all forces exist in pair. If you have forces by rope on block, you should also have another force which is by block on rope. And this force should be in the opposite direction, so you should expect the direction of this force to be pointing this way. So what is this telling us? The moment the rope is pulling on the block in this direction, the block itself is also pulling the rope in the opposite direction. Because if you pull, you experience some kind of resistance, right? So the resistance is because of the block. So the block is actually also pulling on the rope as well. And the direction where the block pulls on the rope will be in the opposite direction to the tension that we mentioned just now. So this is the second scenario. So now we are seeing Newton's third law of motion in action. For different objects, you see opposite pairs of forces in opposite direction. And this follows what we say just now. The action-reaction forces should be acting on different bodies. So you see the action and the reaction pairs exist on free body diagram of two different bodies. Okay, we move on to the third and fourth situation. So for external force, you see the human is pushing the box. So in this case, for the free body diagram of the block, you should observe there's a force by the human on the block. But because of Newton's third law of motion, you know that for the free body diagram of the human, you should expect the block to push back on the human towards the left hand side. That's why when you're pushing a block, right, you feel some kind of resistance by the box. It's because the box itself is providing a counter force, a force in the opposite direction. That's why your hand don't just move like that. Your hand feels some kind of resistance because the block itself is providing an opposite force to push you back. And this is the force shown on you. It's exerted on you as a human. Okay, the fourth situation, normal force here, we know that this normal force is pointing upwards, it's perpendicular to the surface, and this force here is exerted by the floor on the block. So the floor here is pushing upwards to support the block, preventing the block from falling, right? It's pushing upwards. So what does it tell you? If we know Newton's third law, we know that if we have a force by the floor on the block, then you should also have another reaction force by the block on the floor. So this block itself will also exert the force on the floor because action and reaction pair. And this direction of force should be opposite the direction of the normal force you mentioned just now. So we should expect a normal force exerted by the block on the floor pointing downwards. And that's what you can imagine, right? If you are a floor and you have a block sitting on you, you feel some kind of being pushed downwards, right? You feel some force being pushed downwards, right? So this will be the force experienced by the floor. The force experienced by the floor. The floor experienced a force due to this block. So it's by block on floor. Okay, so you have to be very clear what is by. By is the one that exerts the force. On is the one that experiences the force. So these two things form an action and reaction pair. So for the last scenario, the friction scenario, well, the friction is exerted by the rough surface, right? So for this one, we have our static friction exerted by the floor on the block. This block here is experiencing a force, a frictional force due to the floor. The floor exerts the frictional force. The block experiences the frictional force. So you know Newton's third law of motion, you should see an opposite force, and this force here should be exerted by the block on the floor. So the floor itself also experiences a force, and it's also a friction force, but this one is exerted by the block on the floor, and it exists in opposite direction, same magnitude. Last situation, kinetic friction, is similar to the situation for static friction. If you experience a frictional force exerted by the floor on the block to the left, then you should expect the floor should also experience a force by the block on the floor, and it should be pointing in the opposite direction, which is to the right. Okay, so the conclusion I want to make is every forces should exist in pair. We usually focus on what is exerted on our object of interest, but we have to be aware that actually there's a force that is exerting in the opposite direction on the object that is exerting the force on our object of interest. If something is exerting a force on us, we have to know that we are exerting a force on that something as well, because all forces must come in pairs. So that's the explanation for Newton's third law in various situations.